Okay, so now I'm recording on Zoom. All right, sorry. Back to notes. So last class we talked about the principle of work energy. And we learned that this very important equation, of course, that I just lost. This very important equation involves kinetic energy and work done between 2 points of displacement. Okay, so I have a T1, which is the kinetic energy at time 1, or the initial kinetic energy. I have the work done, or the work done by all forces on this body from point 1 to point 2. And the sum of those two things is equal to the kinetic energy at time 2. Okay, some important notes to recall. When did we say that this equation is good for? Like, what are some indicators that we should use this on a problem? Any ideas? Yep. Okay, yeah, so when we need to either know about a change in displacement, or it's asking us about a change in velocity happening after some known displacement. Okay, so this equation is good for, really good for problems asking about a change in velocity after some known change in displacement, or vice versa, right? We could be given the change in velocity and asked about the change in displacement. Okay, so our intro for today here is that with the equation set from last class, we're going to learn a new term today that for whatever reason seems to retroactively confuse people. Okay, so today we're going to learn about this concept of conservative forces. And it's important that you realize for the principle of work energy, we do not need to worry about, quote, conservative forces. For the principle of work energy, we don't need to worry about it. However, for the conservation of energy that we cover today, conservation goes with conservative forces. So when we do the conservation of energy equation, we have to make sure that the only forces that are doing work on our system are conservative forces, and we'll talk a little bit about what that means. Okay. So work energy has no sort of hidden dragons. Conservation of energy does. All right. So let's hop on in. What the heck is a conservative force? There's a formal definition of what is a conservative force that I find to be rather vague and ambiguous, and it's kind of hard to understand right off the bat. What matters more for you in this class is that I'm going to tell you what are the examples of conservative forces that we will work with, and I will give you the examples of non-conservative forces that we will work with. And you need to be able to classify basically these four types of forces into conservative or non-conservative. Okay, so conservative force is when the work of a force is independent of its path and depends only on the force's initial and final position on the path. Okay, so some examples of conservative forces. We've actually already seen both of them. Weight is a conservative force, right? So when we took the work done by the force of gravity, we cared only about the initial height and the final height of our object. In no way did we at all consider anything that happened between those 2 points. Okay? So we only cared about the initial and final height for weight, and then also spring force is also conservative. So the force by a linear Hooke's law spring. Does anyone want to take a stab at a non-conservative force? Yep. Beautiful. That is like the #1 example. However, we will also see in this class sometimes externally applied forces, and I'll draw a picture to show what that means. For example, let's say you have maybe like a mass spring damper system or a mass spring system, and you have this kind of magical external force F being applied to M, and you're told nothing else other than we have this external force F being applied to the mass M. That F, we cannot treat that as a conservative force. That will have to be treated as a non-conservative force. Okay? So external forces are non-conservative. I'm going to erase that because I need the space. Okay, let's talk about energy. So energy is the capacity for doing work. And there are many types of energy that you've probably heard before since maybe elementary school. Can you name some types of energy? Kinetic, beautiful. Potential, okay. What are some examples of maybe potential energy? Are there other like examples of potential energy? Gravitational potential energy, spring potential energy. Anything else? Electric, I think you're meaning more like batteries, which is actually a chemical potential energy. There are chemicals that do a chemical reaction that causes that voltage supply. Yep. So for this class, the only sources that we will worry about are the general classifications of potential energy and kinetic energy. And for potential energy, we will only worry about gravitational and elastic, so spring potential. Okay, so for potential energy, we will have gravitational potential energy. And we will say that gravitational potential energy, V due to G, is equal to the weight of the object times the height of the object. Bless you. Elastic potential usually from a spring. The elastic will equal positive 1/2 KS squared. Now, why do I put the positive here? It is always positive. Very good. Is gravitational potential energy always positive? It turns out no. It depends on where you set your datum or your reference height. Okay. Okay, kinetic energy. We can have two types of kinetic energy, although we're only going to deal with one today. We have translational motion. If an object is translating, then its translational potential energy, sorry, that looks like a tau, I don't want it to be tau, is equal to 1/2 mv squared, where v is the speed of that object. And then next class, we're going to learn about rotational kinetic energy due to rotational motion. And this one is only for rigid bodies. Okay, so kinetic energy due to rotation is equal to 1/2 I. What do you think it is? If it's very, very parallel to translational, what should be the next term? Omega squared. Yep. Right? So one is translational velocity, the other is just rotational velocity. So this is angular speed. Question? Yes, it is. Yep. So very, very similar. Again, mass moment of inertia is parallel to what for translation? Mass. Yep. So one is the resistance to translational acceleration, the other one is the resistance to rotational acceleration. Very good. Okay, so here's our big equation for today. And I'm doing this in red, in bold, I'm gonna highlight it because I don't know how else to make it extremely clear that this equation can only be used in a very special case. And that case is if and only if only conservative forces do work on the system. If and only if. Okay, so if there's friction doing work on our system, we can't use this equation. Friction is right out. Okay. We get this equation called the conservation of mechanical energy. For a single particle, it looks like this. Kinetic energy at time 1 plus potential energy at time 1 equals kinetic energy at time 2, or sorry, I really should say position 2. At position 2 plus potential energy at position 2. Kinetic energy at point 1, potential energy at point 1, kinetic energy at point 2, potential energy at point 2. If we have a system of particles, we just throw summations in front of everything, and we sum up all the kinetic energy of all the particles in the system. plus all the potential energy of all the particles in the system equals the same for time 2, or position 2, I should say. Questions so far? Yeah?
You said at the beginning of the class that we did not, in the T plus sum of U equals T2, like the one from before, that we did not need to worry about conservative forces.
Correct.
But didn't we use weight when we calculated this earlier?
It is a conservative force. The thing is that we are still allowed to use this equation when friction is doing work. Because friction is a non-conservative force, which means that we could not use the conservation of energy equation, but we can use this one. Yes. You don't need to worry about like when you're allowed to use this or when you're not allowed to use this. You can always use this. You can't always use conservation of energy. Yeah, I can see how that's not worded great.
You don't need to worry about the concept of conservative.
Yes. In other words, this equation is still valid even if non-conservative forces like friction are doing work. Okay? Always valid? Today, not always valid. We're going to see, the reason I'm harping on this is we're going to see a very, very similar set of ideas when we go to impulse momentum. The impulse momentum equation always works. Conservation of momentum doesn't always work. Okay? Here, principle of work energy always works. Conservation, not always. Whenever you hear the word conservation of, or the equation that goes with that word, be cautious. Okay. All right. We ready for an example or two? Let's do it. All right. First example, I'll try to make it bigger. The spring is unstretched when S is equal to 1 meter, and the 15-kilogram block is released from rest at this position. Determine the speed of the block when S is equal to 3 meters. The spring remains horizontal during the motion, and the contact surfaces between the block and the inclined plane are smooth. Okay, so obviously today is the conservation of energy day, so you're probably like, yeah, we're going to use the conservation of energy equation. Why is that valid here? Yeah. There are only conservative forces doing work on this body. Okay, so we've got a spring. We can draw a free body diagram. In fact, let's go ahead and do that. Let's draw a free body diagram, and we'll go force by force and ensure that only conservative forces are doing work. So, sorry, I'm going to try to do a little bit better of a habit of writing out my known. Let's do known first. The spring is unstretched at 1 meter. We'll need to know that. So when S equals 1, the spring is not stretched. The mass of block A is 15 kilograms. The initial velocity of A is 0. Why is it 0? What words say that? Release from rest. Yep, release from rest says initial velocity is 0. Determine, so find the speed of the block when S equals 3 meters. The spring remains horizontal during the motion, and the contact surfaces between the block and the inclined plane are smooth. So smooth equals no friction forces. Okay, there's my known, there's my find. Now let's do the free body diagram. I've got this block A that's on an incline. I've got this spring thing connected to the center. Got a normal force from the plane. And I've got some weight that's 15 kilograms times 9.81 meters per second squared. All right, is weight a conservative force? Yes, it is conservative. Is spring force a conservative force? Yes. Is the normal force a conservative force? It doesn't matter because the normal force is not doing any work, right? So this block is only going to move in the direction of the inclined plane, which is exactly perpendicular to the normal direction. So it has absolutely no movement in the direction of the normal. So there's no work done by the normal. So it doesn't even matter whether the normal is conservative or not. Okay. Okay, so only conservative forces forces are doing work. So we can use conservation of energy equation. Okay, I'll rewrite that equation. We have kinetic energy at time 1 plus potential energy at time 1 equals kinetic energy at time 2 plus potential energy at time 2. Tell me about kinetic energy at time 1. Why is it 0? It's released from rest. Beautiful. Okay, tell me about potential energy. What are my sources of potential energy at point 1? Right? So we have the weight. You're probably thinking, do we have any potential energy by the spring, but not at point 1 because it's not stretched or compressed at all at point 1. Okay, so the only thing contributing here will be gravitational potential energy. So we'll need to fill out what that means. Tell me about kinetic energy at point 2. Yep. Yes. Yep.
Do we know that S is equal to 1? Okay, wait, no.
We do. Yes. At S equals to 1,
Spring is
spring is unstretched.
And we want to
And
know
we
about
will-
what happens when S equals to 3.
I want to know about what
Yes,
happens
question,
when
please.
S equals to 3. Yes, question.
Yes. So as the block goes
Yes.
down, the spring does not
Yes.
rotate.
So as
it
the
just
block goes down, the
straight
spring does
down
not
with the
rotate.
block.
It just goes straight down with the block.
So tell me about kinetic energy
Okay.
at point 2.
So tell me about kinetic
when
energy
S
at
is
point
equal
2.
to 3. Do we have any
When
kinetic
S is
energy?
equal to 3. Do we have any kinetic energy?
Yeah. So is it due to translation, rotation,
So is
or
it
both?
due to translation, rotation, or
Just
both?
translation. We're just doing particles today. So we're
Just
gonna treat this
translation.
block
We're
as
just
a
doing
particle.
particles today. So we're
Okay.
going to treat this
So
block
we'll
as a
have
particle.
translational
So we'll have
kinetic
translational
energy.
kinetic energy.
And then will we have any potential
And then will we
energy
have
at
any
point
potential
2?
energy at point 2?
Just what?
Just spring.
Just what?
Just the
Just
spring. Why just the
Just
spring,
the
Samuel?
spring. Why just the spring,
Do we
Samuel?
know for a fact that it's
Do
going to
we
go all
know
the way
for
to
a
the
fact
ground?
that it's going to go all the way to the ground?
Where ours, where gravity are.
We Yeah, beautiful.
We-
Sorry to cut you off.
Yeah,
Yeah.
beautiful. Sorry
We
to cut
get
you
to
off. Yeah.
choose
We get to choose where we consider our datum point for zero potential
Okay.
energy.
Well, I'll draw
Okay.
exactly
Well,
what this
I'll
means
draw
when we go
exactly
into the
what this
details
means
here.
when we
But
go
essentially,
into the
we can
details
consider
here.
wherever
But
it
essentially, we
ends
can
up,
consider
that's the
wherever it
point where
ends
we're
up.
gonna kind
That's
of
the
consider
point where
zero
we're going
potential
to
energy from
consider
gravity.
zero potential energy from
So
gravity.
we will have no gravity
So
potential.
we will have
but
no
the spring
gravity
will
potential,
become
but the
stretched.
spring will
So we
become
will have
stretched. So we will have spring
potential energy here.
potential energy here.
Okay. Let's
Okay.
try to fill out some
Let's
of
try to
these,
fill out some of these
details.
What
We'll probably
what
need to do
we
is draw
will
a really
probably
nice
need to do is
picture
draw a
of-
really nice picture of.
Oh, that was terrible.
Oh, that was terrible.
Of the two
Of
positions
the two
of this
positions
block.
of this block.
So I'm
So
gonna
I'm gonna
draw
draw
maybe
maybe
A up at the top here.
And my spring, let's say this is S equals to 1. And this is my spring at point 1. And then I'm going to draw the second position. This will be position 1. This will be position 2. Well, the spring will become stretched. And S will be 3 meters. Okay. So like I said, we get to set our datum for the position of zero gravitational potential energy. So let's set our datum here at this final position so that at point 1, I have gravitational potential related to this height, and at point 2, I have zero gravitational potential. Okay, so then the question becomes, what is this height? We're going to have to figure out what this height is. Any ideas on how to find that?
Not say very bottom,
You could equivalently. We're going to do the same thing. It doesn't matter whether it's at the bottom or not. Right? Like there's actually no way to tell whether it's at the bottom because we don't know the overall height of this thing. But it doesn't make a difference to the problem. So we can still do trig though. How do we do trig? Right, so this is 30 degrees, which means that, whoopsies, which means that this is 30 degrees, and also that this is 30 degrees. Okay, so I can find out what is this overall side length using this 3 meters and this 30 degrees. And then I can subtract out the little part at the top using the 1 and the 30. Okay, so let's try to find this height h. This h is going to equal the total minus the little bit at the top. So we should say, let's see, y total, we'll need to use sine of 30. So sine of 30 equals y total over 3, or y total is equal to 3 sine 30. So this is 3 sine 30 degrees. And this y top should be 1 sine 30 degrees. Okay, so my thinking is that we have 2 sine of 30 is h. Okay, so our initial gravitational potential energy, if we go back to our gravitational potential energy, we should have the weight times the height. The weight of this thing is 15 times g. And that's the full left-hand side. That's my V1. Okay. How can I write my potential, or sorry, my kinetic energy at point 2? What's my equation for 1/2 mv final squared? Good. The mass is 15. I'll go ahead and plug that in. Very good. And that's what it's asking us for, right? It's asking us to find V1s equals to 3 meters. Okay, and that's added with, I no longer have potential energy from gravity at point 2, but I do have some spring potential. Let's go back to my spring potential equation. I have 1/2 ks squared. 1/2 ks squared, where k here is the spring stiffness, which is 75 newtons per meter. And then what is the stretch? How can we find the stretch? Samuel? Absolutely. We can do trig again. Right. So we can say that the stretch is equal to whatever this length is minus whatever this length is, right? Because this is the relaxed length, so that length does not count towards our stretch. So we'll need to do, let's see, maybe x final minus x initial. So stretch equals, so that would be 3 cosine 30 minus 1 cosine 30 equals s. So I should just get 2 cosine 30. Okay, and I'll plug that in for my stretch. Stretch is squared. Okay. This is looking pretty good. Why am I happy with this? Beautiful. One equation, one unknown. Better yet, that unknown is the thing the question is asking me for. Solve one equation for one unknown, and this problem is done. Okay? All right, so final answer here should be that V final is equal to 2.15 meters per second. Questions on this problem? Okay, we got another one. And as usual, I'm going to give you a little bit more leeway here, although it is going to be a little bit tougher. Okay. If the spring is compressed 3 inches against the half-pound block, and then the block is released from rest, Determine the normal force of the smooth surface on the block when it reaches the point where x equals 0.5 feet. Okay, so there's a very key difference between this problem and the previous problem. And it has to do with what it's asking you for. Here they're asking you to find a force. Right, so that means we're going to have to do kinetics. We're going to have to sum forces equals to mass times some acceleration. We didn't have to do that last problem because it was asking about a velocity. It was only asking about the kinematics of the problem. Okay, so now we're going to have to do the kinematics part of the problem and then do the sum of forces equals mass times acceleration part of the problem to use those kinetics, or sorry, use what we know about the kinematics to solve for the forces that are involved. Okay. Another key thing here, when we start to think about sum of forces equals mass times acceleration, we need to think probably about what coordinate systems make the most sense here. So it turns out that it will be easiest for us to write accelerations in terms of a normal and tangential coordinate system. Actually, I don't need to write this for you because I already wrote it up here. Okay, so I'm going to remind you of what acceleration looks like in normal and tangential system. And then they give us the equation of the curve that this particle is following. They give us that equation so that we can solve for the radius of curvature at that point. So we can solve for rho, and I've given you here the equation for how we find rho based on an equation of the curve. Okay, so here's maybe the game plan, what the game plan should be. This is you should go through the song and dance of convincing yourself that the conservation of energy equation holds. But the first part will be to use conservation of energy. To find the velocity of the block when x equals 0.5. Then use that velocity to write the acceleration in normal tangential system. And then finally, sum forces in the normal tangential system to solve for your normal force. Okay, I'm going to leave you now to try to take a stab at that. If you get stuck, please raise your hand and I will try to help you get unstuck so we can keep moving through this problem. Is Chase here? Carlos? Carlos? Yeah? Is Will McGonigal here? Seth Young? There's Samuel Wu? Brian Sutton, Daniel Rodriguez, Brian Maria, Benjamin Lewis, Ethan Nines, Nanoko, Andrew Hoffman, Jack Goldhaber, Tanner, Matthew Fielding, Jamie Lanier, Franklin Ando, Seth Young is not here, Tommy Rodriguez, Robert,
Can we assume that it's a pound force that they give us there?
You always assume that pounds given are pounds force. To get mass, you have to divide by 32.2. Yes, question.
Well, it says, well, you just assume that's,
Yes.
but there has to be an initial velocity. I also okay to assume that there's no.
There does not have to be initial velocity. So what does it describe? It says the spring starts out compressed against the half-pound block. Right? So it starts out with zero velocity, but all of this potential energy from the spring. So the moment you let it go, the spring flings it off to the right. Okay. Is there any initial kinetic energy? Zero. Yes, absolutely. Because it starts from rest. Is there any potential energy at point one? Yeah, Leah? The spring potential. is there any kinetic energy at time 2? Yeah, we said there's probably still some velocity as it goes up this slope, right? So, yes, 1/2 mv squared. Is there any potential energy at time 2? Just gravity, right? Just gravitational. Okay. This is a really good intermediate step to put it into words first, and then go find all the equations that go with each of these sources. How should we figure out the height? Yeah. Squared. Yep. Absolutely. 1/2 x squared is the height. And we know that it's asking us about x being 0.5 feet. Okay. So this is 1/2 x squared. So this is plus 0.5 over 32.2 times 32.2 times, ran out of space, 1/2 0.5 squared. Yes, Leah? Yep.
Like it starts at 3.
So it's only relevant to the point, the immediate point that you're worried about. So at point 1, I only want to know how stretched or compressed is the spring at point 1. If I am still stretched or compressed at point 2, I will have a continued spring stretch or compression at point 2. Can't wrap your mind around what part?
The last year.
Okay, from the previous problem?
No.
Oh, this one. Okay, yep. The 0.5 over 32.2? Yeah. So whenever we have a pounds given in a problem in this class, we assume that is pounds force. The only way to go from pounds force to pounds mass is to divide by the gravitational constant. Okay? So unlike with kilograms, kilograms is the mass. To get to the weight force, we have to multiply by G. Leah? Okay, yeah, we do need to be careful because, sorry, this 0.5 is in feet. So I would actually, instead of doing 0.5 feet, I would probably say that that's 6 inches. Convert everything to inches. Or convert everything to feet, but I think going to inches is easier. Other question? Same thing? Yeah, it'll just give you the height as inches. It'll give you y in inches. Yep. Question?
Is the Y equation, is that like, plug something in that's feet?
Yes, if you plug in feet for x, you'll get out feet and y.
So when you calculate rho, then is that answer also in feet?
It depends on what you plug in for x.
Say you plug in.
X in feet,
Yeah.
then you will get out rho in feet. Yep. Okay, so what do we get for the final velocity? Did you change to the 6 inches instead of the 0.5 feet?
So, okay.
Hold on, let me double check something. Yeah, so the 15.2 would be if you did it all in feet, which we can certainly do. That would just be, instead of 3 inches, it would be a fourth of a foot. And this would be 0.5. Does that make sense? Yep, question?
So, like, so we're switching back to feet because this isn't a unit for gravity, feet, is it feet per second?
Yeah, okay, yeah. So we really should move to feet instead of going to inches because of the gravity being in 32.2 feet per second squared.
Like, you would want it to be there, all that.
Yeah. Yep. Sorry, I shouldn't have suggested going to inches. I know, why the heck do we use these units anyway? Okay, so we should get 15.27 feet per second is the final velocity when we're at the point that we care about. What's our next step? Now we want to use velocity to write acceleration in terms of the NT system. Okay, so I'll go grab this equation. Come on, pen work. Copy. Paste. 2. Use VF to write A in NT system. Come on, iPad, work with me. Okay, so we should get acceleration is equal to V dot. I don't really know how V dot is changing. So let's maybe leave that as is for now and say that the normal direction is 15.27 squared over rho, and I need to go find rho. So let's grab my row equation. Okay, what is y is equal to 1/2 x squared? So dy dx should be x, d squared y dx squared should be 1. Which means that rho equals 1 plus x squared all to the 3/2 over 1. And where do we care about? Well, we care about when x equals to 0.5 feet. So rho, when x equals to 0.5, should be 1 plus 0.5 squared all to the 3/2. What do we get for that one? Yes, Micah? Dude, the unit conversions on this are killing me. Yes, that's in inches. Okay, so 5 pounds per inch times 12 inches in 1 foot equals 60 pounds per foot. Thank you. I appreciate it. Okay, what do we get for rho? Beautiful. 1.39 something feet, which means that the normal component of my acceleration has this here, 398. Okay. It turns out we really only need to know the normal direction. So use acceleration in the normal direction to find normal force. So let's draw a free body diagram of this block. When I am on this surface, I'm kind of tilted this way. I've got some weight, which is 0.5 pounds, and I've got some normal force. Do I have any friction? That or not, or we did the whole first part of the problem wrong. No friction, smooth surface, anything else? No? Okay, those are the only forces involved. My U hat T goes this way. My U hat N goes this way. What if I said the sum of forces in the normal direction equals acceleration in the normal, which is 15.27 squared over 1.398. There's still a trick hidden here. What am I missing? How the heck do I sum my forces in the normal direction? Yeah? Sorry, say again? Yep. Thank you. Very good. I'm still missing something. Theta. Yeah. I can't do the trig for how to split up this weight force into a normal and tangential component until I know the angle this is at. Any ideas how we might figure that out? Yeah? Theo? Or not Theo? Theo? Oh, yes.
I think it's very difficult. Equation, plugging in your x value and you see the rise of the.
Yes. Beautiful, beautiful. Okay. So this is what happens. When we take the derivative dy dx, we're finding the slope of this curve at the very instant where x equals 0.5 feet. Okay? So if we were to take that slope and turn this into like an instantaneously flat surface, we can find the angle that that instantaneous slope is at. Okay, so it says that the slope, our dy dx, is equal to x, which is 0.5 feet. That's the rise over the run. So x, y, rise over run. The y component over the x component equals 0.5. What's next? What do I do next, Theo? How do I go from knowing this slope to knowing this angle?
Tangent, opposite over adjacent, inverse tangent.
Right. So opposite is y, adjacent is x. So tangent theta equals y over x equals that slope 0.5. Okay, so theta here equals tan inverse of 0.5, which should give us something like 26-ish degrees. 26.56 degrees. Okay. I still need to split this weight into components. So we've got a weight and we've got a slope. This is the angle that defines the slope. So this angle is also theta. Yep. Question?
Can you plug in the x value into the like formula and pull the y value out? It gives you a different answer. Like if you plug 0.5 into the y.
That just tells you how high up are you when x is 0.5. It doesn't tell you the slope of the line at x equals 0.5.
That's like I came to that, but that's still like y over x. Yeah, it just doesn't make any sense. Sam's killing himself over here.
If you put 1/2 x squared all over x, you get 1/2 times x, which would be 0.25 in this problem.
Okay, but what you're describing is like 0.5 is the distance from like this origin to my block, and then the height of that block at the moment, which is not the same as taking the local derivative of that path and finding how much that path is tilted. Yeah.
Are we doing that with the force of gravity?
Yeah, we have to split the force of gravity into the normal and tangential component in order to sum forces in the normal direction equals the normal acceleration. Okay. Yep. Mhm. Okay. All right, let's keep going. So this would be, oh, no. I drew the normal direction in the wrong direction. It needs to go into the curve. It curves upwards. Okay, so this is the right triangle I care about. So we can say W as a vector equals mg minus mg sine theta in the tangent direction. minus mg cosine theta in the normal direction. Okay, so if I go back to summing my forces in the normal direction equals mass times acceleration in the normal, I should get the normal force minus, sorry, normal is actually going to be in the positive direction. Yep, minus the weight cosine theta equals mass times v squared over rho. Why am I happy? One equation, one unknown, and the unknown is the one the problem is asking me for. I just need to solve for n. Anyone have an answer for n? I got 3 and some change. About 0.04 and change. Ounce. Okay, I apologize. I made way too many the unit conversion issues, but these are the correct answers for switching to feet. Let's see. Please, please, please do not forget to bring your project module 1 printed to class on Thursday. Okay? We will peer grade. We will remediate any disagreements. We'll turn those into me and I'll upload grades to the gradebook. We're also doing the experiment in class on Thursday.
I had a question.
Yes. Yes. Correct. You will not actually, you don't need to draw the free body diagram. It's not necessary. But there would be an equal and opposite normal force
And the friction is the same direction.
as the motion. Well, okay, so this is gonna try to, this moving is gonna try to push this thing to start moving in the same direction at that contact point. So your friction is actually gonna be going that direction and it's gonna cause E to start rotating that way.
Okay, thank you.
I also had a question about how did you break it? Can you sort of break it down? Like the way
Yeah, you have your, this line is not quite right. We want there to be like a 90-degree angle here so that the leg, one leg goes in the tangent direction and the other leg goes in the normal direction. Okay, so I'm saying that this is perfectly parallel to the tangent and this is perfectly parallel to the normal.
So
Does that make
that's,
sense?
yeah. So then you're looking at trying to, all right, so
Yes.
the normal, so I guess what you said,
Is the one that goes along the normal. And if you follow the direction of weight, it goes that direction, right? Just opposite the positive normal unit vector. So it's a negative u hat n.
Okay. And then when it comes to some of these,
Yeah.
is there like something I can like print out because I'll be on a cruise, so I don't know if I'll have like service.